Hello, my name is Charles Wade. I am a PhD student at the University of Colorado Boulder in the Matter Assembly Computation Lab. Today I'm going to be going through a sort of hello world and getting started to our project OpenVCAD. So to get started, we're going to look at the OpenVCAD public repository on GitHub. So this repository holds some of our getting started information, language documentation, as well as a compiled version of the application. If you're looking for the open source code for OpenVCAD, I'll talk about that a little bit later. So to get started, I recommend coming on here. The README has some basic information about getting started, a link to the full paper if you want the technical details. But to get started using OpenVCAD, I recommend going to the wiki. So on here, it'll talk about installing OpenVCAD. So right now, we provide just Windows executables for OpenVCAD. If you're interested in another operating system like Linux or Mac, just talk to us and we might be able to build those for you. So to get started, I recommend going through this installer information. Go ahead and going to the releases, downloading OpenVCAD, and opening it up. So once you've done that, we can move on to the getting started information. I recommend looking over the conceptual overview, as well as the GUI application, material definition files, those sorts of things. But I'd like to just go ahead and jump in and show you how to actually prepare some designs in OpenVCAD. So if we open the application up, you can see it's a pretty straightforward UI. On the left side, we're going to have our code editor. On the right side, we're going to have a render preview. Down here at the bottom, we have sort of an error console, and then we can select our material definition file here. This material definition file basically assigns material names, so perhaps red, blue, or maybe tango or PLA to actual colors when we go ahead and slice this into bitmap stacks. So you can see when we start up OpenVCAD, all OpenVCAD scripts start with this root tag and these three sort of tuples of numbers. So this first one represents the minimum sample coordinate in the design, the maximum, right? So these are really the corners of a bounding box, and then this will be our voxel sample resolution. So when we export this, this number as well as the dimensions will determine how big our images are. So generally speaking, you probably want to set the voxel sample resolution to match whatever your voxel resolution is on your printer. And you'll want to match these numbers with whatever the size of your designs are. So to get started, we're just going to open up a basic design. So we've got a file, OpenVCAD file. I'll just do a hello world here. Looking at the actual OpenVCAD script that gets open, if you go through the language documentation and the getting started, it'll talk about more of the specifics. We use 2 forward slashes like C++ or Java to define a comment. So all of this is commented out. It'll be ignored by the compiler. Using this tree structure, we're going to nest the different nodes to build our object. So if I want to visualize this, I can come up here to View, and then we get 3 different options. So these visualization techniques depend on your system. So if you have an NVIDIA CUDA capable GPU on your system, you will see this render with GPU or render with ray tracing enabled. This is GPU based. If you don't have that, then this option will likely be grayed out. Rendering with voxels is a little bit resource intensive. It's going to be slower, but it'll work on all systems. So we'll start there. If we click that, we're going to see the design updates here in the left. We can click with our left click on our mouse to drag around and view the object. We can zoom in with the scroll wheel. We can pan with the middle mouse button. So here we've got a visualization of the object. We're looking at the individual voxels that got sampled, but it's important to note, and if you kind of read the paper, it'll talk more about this. The actual design itself is an implicit representation of this, right? The voxels are merely an artifact of the, visualizer, right? They sort of a necessity of being able to visualize this, at least in this form. I'll show you what the other visualizations look like in a minute. But first, let's look at what this actual design looks like in the VCAD script. So I, generally speaking, recommend working from inside out in OpenVCAD. This is because of that tree structure. So in this case, we kind of dive in here we can see we have a bunch of comments. We can see we have sort of a cube here defined with a quote red material, a sphere defined initially with a red material. The cube, the 4.0 is the side length, 2.5 is the radius. And when we actually look at this object, it kind of looks like we have a cube with the sphere subtracted out of it. And that's because we're using the difference operator up here. So the difference takes two child trees. So in this case, we just have leaf nodes. We could have entire subtrees beneath this. In this case, we take the cube geometry and we subtract out the sphere geometry. And the result is this difference node. And since that's all of our design, that gets put into a root node. Up here, we sample it, in a big enough sample resolution. So in this case, -5, -5, -5 to +5, +5 is going to be enough. Give it a reasonable voxel sample resolution, and that's what will net our object. So you can see this is pretty straightforward. We defined both of these with a default material. In this case, we actually only use the red material because we're subtracting the cube or subtracting the sphere from the cube. We ignore the sphere's material. We're only going to result in cube geometry, so we're only going to have red geometry. If this was a union, for example, we combined their two sets of geometry and they had dissimilar materials, then that would cause a different effect. We'll talk a little bit about how that works in a minute. So let's talk about some of the other ways we can visualize. So if we come back up here, we can render as an isosurface. So that's going to go ahead and render as a mesh. We can click that. Okay, so let's talk about some of the other visualizations. So the other primary one I'm going to show you right now, we do provide an isosurface. If you look at the presentation, the PowerPoint presentation I give about VCAD, you can see kind of an example of it. I won't show it here because this object is not very interesting to look at it with it, but if your object gets particularly large, the isosurface is a faster way to visualize that. If you do have an NVIDIA CUDA-capable GPU installed in your system, you can use the ray tracing. So if you go ahead and click that, it's going to bring up this window, and then it's going to process it. That would normally have a progress bar, but this is a pretty simple design, so it renders pretty quick. So you can see now we have a very similar kind of looking object to what we had before. It looks a little nicer. We've got shading. But what's really powerful about the ray trace visualizer is the ability for us to control the transparency, right? So it went ahead and switched us over. So before we were on this OpenGL preview, we've now switched over to this ray trace. You can swap back and forth. This has a whole lot more kind of fine-tuned controls for visualizing multi-material objects. In this case, we have that single material one, but we can control the transparency, so we can kind of fade this back and peer in the inside. In this case, we only have red, so it doesn't net as much. We can also control the lighting, at different angles, as well as sort of animate the actual visualization of this object. So this kind of represents how it'll be 3D printed. Okay, so one other thing you can do with this preview is select a render quality. So depending on what you do, so like let's say we select low and render again, you can see our fidelity gets a lot lower. For simple designs like this, it's not necessary. It is only going to take a couple seconds to load anyway. This can also be GPU dependent. If we were to turn this up to ultra and render it, you can see we're going to take a little bit longer to actually go ahead and sample this tree into a voxel structure that we can visualize. So it should be noted, much like the first preview I showed you, this also samples into a voxel tree or a voxel grid that we are ray tracing. So let's go ahead and look at another example file. So if we come back, let's look at the types of geometry we can use. So I'm going to just go ahead, we'll turn this back to high, and we're going to render with ray tracing. So here we can see several different geometric objects, all in different colors or different materials in this case. So kind of starting at the top here, right, we have a rect prism. So this is a rectangular prism. That's what we see along the red here. We can tell that by the red. The rect prism is defined with a tuple. of 3 values. So 65 is the length, 5 is the depth, 1 is the height. So in this case, OpenVCAD uses millimeters for all of its units, so this is defined in millimeters. You can see we end up chaining that. These sort of squiggly brackets say, okay, this is a child of the translate node, and all we did was translate it kind of down, right? So all geometric primitives in OpenVCAD are created about the origin, and then we have to apply transformations, be it translation or rotation or scaling, to get them where exactly we want them to be. So moving down, you can see we define a sphere. So in this case, a blue sphere, and you can see in the design we have a blue and a green sphere. I'll talk about this blue one, and then I'll talk about the green one and how it's defined differently. The sphere node's pretty straightforward. This 4 represents the radius. Once again, like all geometric primitives in OpenVCAD, we have to give it a default material. So in this case, it's blue. So this other sphere is going to be defined in the function node. So the function node allows us to define a scalar field, right, or a signed distance field, really. So in this case, we define the equation of a sphere just in plain text, so x squared plus y squared plus z squared minus some radius squared. In this case, it would be 4 squared or 16, along with our material name. So this one's green. Right, so if you go to the documentation, you can see the 3 coordinate systems we support. So in this case, it's Cartesian, spherical, and cylindrical. You have special variables you can name that represent those coordinates in any given expression you define in OpenVCAD. So in this case, that's x, y, and z. It could be cylindrical or spherical coordinates. Once again, we translate this function on top of that because we defined this function around the origin. Now, had we shifted this function, applied a transformation within this expression, it would have been defined there. OpenVCAD doesn't do any extra centering. It just samples this function wherever we want it to. The final piece of geometry is this OpenVCAD text we see floating here, defined in the cyan color. This is defined using a mesh. So in this case, I designed this OpenVCAD text as an STL file, and then I just import it as a mesh. Now, when I designed this file, I designed it in Fusion 360, which had it about a different coordinate axis. So in this case, I actually applied 180-degree rotation. These rotations use degrees in OpenVCAD. To actually get it rotated to our viewport and to make sense. This triangulated mesh could have been saved as a 3MF or an OBJ or various other triangulated mesh formats. And then finally, you can notice that all of these nodes are children of the root node. So this is an important fact in OpenVCAD. The root node is what is effectively a pseudo-union node. That is to say, you can have as many children as you want in this root node, and they all just get combined into one VCAD design, right? So this will be considered one design. When I export this as bitmap stacks, I'll be able to do that as individual slices. Speaking of that, how do we export this, right? I want to take this to my printer now, right? So we come up here to export, and you can see we have several options. PNG stack being probably the most relevant. You can also export to OpenVDB or NanoVDB grids. Same thing with BinVox or binary voxel. As well as INP simulation files. So if we want to export PNG stacks, we can click on this. It's going to ask us for a path, so we could browse to a location, select a folder. We can give a base file name. So what this is going to do is give sort of a base name, underscore, and then some number, right? So depending on how many layers we have, this could be however many files. So maybe we just say test underscore XX. This will be automatically incremented. And then we can pick our image format based on what our printer requires. So let's just say RGB A 8-bit. We'll hit start export. That went ahead and opened this up. You can see this sort of cross-sectional slices, right? We start with the red, we've got a gap, and then we're going to go ahead and take horizontal slices through our OpenVCAD text. We zoom in, we can see what's actually going on here. Okay, so let's move on to true multi-material sort of functional compositions, right? So if we come back, we'll open up this multi-material example I put together. So this one is going to employ the F-grade node, or the functional grade. So I'm going to go ahead and just visualize this. You can see it's a fairly basic geometry, just a bar, just to show what the gradient is going on here. So you can see we've got a blue material and a red material, and we're kind of grading or mixing these voxels across each other. Now, this is sampled for visualization purposes, but when we actually define these material transitions and internally in the OpenVCAD data structure, these are implicit material distributions, right? So if we look at this F-grade node and kind of dive into it, you can see we have these square brackets, two sets of square brackets. These represent lists. These are n-dimensional lists, right, or n items. We can have as many as we want, but the size of these two lists should always be the same. And what they represent is a unique expression that evaluates for a corresponding material, right? So as we go through this, we say, okay, this function right here, this expression as a function of x, is going to represent our material distribution for the red material. Likewise, this function right here is going to represent our material distribution for the blue material, right? So now you can see why we have to have one, for every expression we define, we need to have another material defined for it. Likewise, I couldn't have made this blue red as well. Everyone has to be unique. So what exactly are we applying here? Well, this right here is a basic exponential cross-grade, right? So basically a sigmoid function as a function of x, right? So starting at 0, this is going to represent 0 is an x-coordinate, right? X is the long axis here, and be assigned to the red material. So on the very far left-hand side, we should have essentially 0 or very close to 0 red. And we can see that. We see maybe a voxel or two, but very, very little red. Likewise, we have the inverse, right? So we've applied this negative x here to sort of invert the coordinate space to allow us to do this. So at any given moment, we should be able to sample both of these functions, or really all functions that get defined in the F-grade node, sum all of the probabilities up across all of the materials and get to a volume fraction, right? So of 1, right? So these represent the volume fractions of our material composition. So one other thing you'll notice here in the F-grade node is this prob, or probability. I'll give you a demo of what changing that does in a minute, but just know for now that allows us to create these gradients, right? And if we zoom in, we can kind of see this mixture applied in practice, right? As we get towards the center, we just have this nice transition. And then finally, the F-grade node gets applied to some subtree. So this could be a bunch of other nodes, potentially even other material nodes. But in this case, to keep it simple, we just have a rect prism, or a rectangular prism node defined. Notice how we gave this a red material by default, but the F-grade node supplants that. It'll completely replace any child distribution beneath it. So let's look at exactly what the probability versus thresh holding mode looks like, right? So if we change this to thresh, and then we render it again, you can see now we have an even split. We don't have any kind of functional gradient. We apply pure thresholding, right? So whatever the majority material is, or the largest component really material is, in this case it would be a majority. If it was more than 2 materials, it would just be whatever the largest component is. That's what material gets defined in that region. So as a function of x, we get to the dead center, right? That's going to be the switchover point, and we get a hard material transition. So this actually does have good applications if you want to define materials in a more traditional sense. You want to have material distributions that aren't functionally graded, but are complicated and based off of functions, right? So instead of traditional design methods where I would design something in Fusion 360 or SolidWorks, assign discrete material bodies to each one of them, then export them, align them in slicing software. Instead of having that difficulty, we can actually just define different material regions very quickly, very easily here in VCAD using thresholding. So one last sort of topic I want to discuss is lattice structures, right? So we'll start with this basic lattice design. Lattice structures in metamaterials are a very popular topic, especially the ability to create multi-material lattice structures. There's very few design methods out there that can do both simultaneous implicit lattice structure representation and material definition and complex material gradients with that. I'll start by just demoing what exactly a lattice structure looks like without a material gradient, but then I'll give you a demo of that. So if we go ahead and ray trace this, we'll zoom out a little bit. You can see we've got a lattice structure here, right? So this is a body-centric cubic lattice that has been tiled across a sort of 2 by 2 by 2 grid. So how do we do that, right? Well, same idea. We have our root node. In this case, I've defined this cubic unit cell externally, so you can design that in Fusion 360. You could export it from other software like in Topology. Export whatever you want your unit cell to be, or potentially define your unit cell using any of the other functional nodes in OpenVCAD. And then we apply this special tile node. So this tile node is going to tell us, okay, this tile geometry should be tiled across all of space. So in this case, we're tiling in a 2 by 2 by 2 grid, but notice how we say we want this to be 10 by 10 by 10. What this is actually telling us here is instead of saying how much we want to tile by, we assume we're going to tile across all of the possible sample space we're in. This says how big the unit cell bounding box is. So in this case, I exported this as a 10 millimeter unit cell, and then I tell the tile node, okay, this is 10 millimeters. That's how far the spacing needs to be to make this work. And then we actually control how we sample this here, right? So we're sampling from -10 in each axis to +10, right? So just by changing this up, let's say we sampled this to 20 now, and then we ray traced it, we've now made it bigger, right? We've added it one extra unit cell in each dimension. So that's how we can control it, just by how we sample things, right? That's great, but one of the things you might be asking is, okay, how do I actually bound that? I want to bound it by a certain volume to fill a specific object. So I prepared this other example here. This will show you how we can do that, right? So if I go ahead and just render this, we can see it. We now have this same unit cell structure, but it fits within the sort of volume of a sphere. So the way we do that in OpenVCAD is pretty straightforward. We do the same thing, right? This code in here is the same. We import our mesh, we tile it in the same exact way, but all we need to do is introduce 2 extra nodes, right? A sphere node and an intersection, right? So the children of the intersection are the tile and the sphere, right? We're taking the intersection of the tile with the sphere, and in this case, that tile is across all of open space, but by taking the intersection of just the sphere, we're able to bound this by a specific volume, right? So in this case, the sphere has a radius of 20, we get a lattice structure like this. If I wanted to make this smaller, I could change this down to 10. We can re-render it. Now we have a smaller lattice structure. If I wanted to make it bigger, I could do that. I could make this, 500, right? This would be a huge lattice, but notice if I went ahead with ray tracing, we're going to be back to this cube structure, and that's because we're not sampling by enough area, right? Here, we're just sampling from -20 to +20. Well, the radius of our sphere alone is 500, right? So we need to have at least really 1,000 by 1,000 by 1,000 millimeter sample to be able to represent this, right? Now, one thing I will recommend if you're working with lattice structures a lot is having an NVIDIA CUDA GPU to be able to render this. It's going to make things a lot faster to be able to do. We can visualize these things with a traditional viewer, but it's going to sit here and compute and think about that for quite a bit longer. Yeah, you can see we end up rendering it. So yeah, that's one thing if you want to render a little faster. So some closing thoughts here with it. If you need to get any help, there's a help button up here. You can report a bug. This is going to open up a new issue, take you right to open up a new issue on the OpenVCAD public repository. You can also, when you do that, please come down here and go to the About. open up OpenVCAD and look at this version number. Please include that version number if you submit any issues. You can also find my email there should you need to contact me directly. And then finally, if you also need help, there's a link to the wiki as well as to the language documentation. If I open that up, it gives kind of a good overview of what's going on here. Talks about the 3 types of nodes. We can go through each node and get a description of what it's exactly doing. And then finally, if you click the check for updates, that'll take you to the releases page on GitHub. You can compare that version number it told you with against whatever the latest released one is, and find any help you might need with that. So one last thing I'll talk about before going is requesting access to the open source version of OpenVCAD. Should you want to do that, if you see the contributing to OpenVCAD section, click here. It'll talk about getting the code. So since VCAD is a sort of a non-commercial product, right, we want to release it to academics as well as hobbyists to hack away at it. We provide the open source code, but you have to ask for access to it. So it's located in a private GitHub repository. If you click this Google form right here, it's going to take you to a page where you can request access to it. You just have to put in your affiliation, agree to the open source license that we have, as well as make sure you include an accurate GitHub username, because that's what I'm going to grant it access to. Just be on the lookout for whatever email is attached to this for a link to accept whenever you're ready.